Yeah, okay. I was asked to give some eccentric presentation, giving some context to the HiDALGO2 in terms of the use cases, in terms of our services. So let's get started from this general slide, where, of course, we understand that our world is interconnected crises, and our planet is complex, and the system is basically under stress. Our changes of the climate intensifies different phenomena like heat waves, droughts, and wildfires. This rapid urbanization we are observing concentrates people, pollution, but also energy demand. These energy systems are transforming, but depend on the weather which is unpredictable. That's why we need to analyze the different scenarios, different possibilities which could cause further analysis. Water, air, and ecosystem react in the ways that ripple across different country borders. So we need to act wisely. On the European level, we must, but in order to do that, we must first understand the complexity, which means we must simulate a different phenomena. But why the simulations matter? Every decision from the city design to crisis response depends on the understanding of the interaction between environment, infrastructure, and the people. Traditional models are too limited to capture this multi-scale and dynamic processes. That's why we need HPC. We need HPC combined with the artificial intelligence, which make possible to simulate these real-world systems in a new real-time. The simulations transform data into foresight, helping prevent loss, optimize energy, and save many lives. It brings us to the digital twins, which are kind of replication of the entire environment, starting from the cities, forests, to rivers, energy grids, of course, everything in silico, simulated. They involve with live data, forecast future states, and test scenarios safely and instantly. In a HiDALGO3, each simulation, starting from the air, through fire, water, and energy building, becomes a part of this larger ecosystem of insight. Together, they form a virtual world for real-world resilience. Of course, we are in the urgency, but it also gives us an opportunity. The decision we are making now of this decade will define the planet's future. HPC power simulations can turn into uncertainty, this uncertainty into preparedness. They help governments better plan, citizens adapt, and industries transform sustainability. These projects, like HiDALGO2, HiDALGO2 is the COE project, Centre of Excellence, unite Europe's scientific and technological excellence to understand, predict, and act properly. And one final remark to this introductory slide, because these challenges are global, so we must be in our acts also global. What specifically is HiDALGO2? HiDALGO2 is the COE project, as Sani said, composed of 9 partners from 7 countries. And our main goal is tackling global challenges by means of HPC, big data analytics, artificial intelligence, and immersive visualization. We're advancing application scalability towards extra scale to efficiently use systems offered by the Euro HPC. We are also concentrating on enriching model capabilities, amplifying some processing patterns and results accuracy. Provisioning of the platform for processing advanced environmental and societal-oriented simulations. We also concentrate on the collaboration with the communities, focus on the similar scientific domains. This will be subject for my final presentation at the end of this session. We're also developing some functionalities which are good subject, good material for the good practice guidelines for the decision makers. If you are interested in the HiDALGO, please visit our website. HiDALGO2 is mostly concentrated on the use cases: urban air pollution project, urban buildings, resource energy sources, wildfires, and the material transport in the water. They have something in the common. They are environmental and the societal. I will tell more about them in the next slide, but this is not all. Yeah, of course, use cases are in the core, but there are a lot of collateral services around. On the left-hand side, you might see input data, like wind measurement, like air quality, land information about the land surface, kind of vegetation. This information are used for feeding the models. Models like weather, traffic, building energy, and shape. And these models are also supported by the number of methods of implementations, applications which are related to the scalability, co-design, and several workloads in order to test the different scenarios, data analytics, and AI, and synthetic quantification, data management. Everything, of course, lies on the layer of the infrastructure composed of the HPC, data analytics supported by the AI, GPU accelerators, and novelty technology. Very briefly, because the urban air pollution, because our use cases like urban air pollution will be elaborated in the next presentation, I would like to draw your attention why these things are important. At the moment, 55% of the world's population lives in the urban areas. It grows. Yeah, we are noticing 6.7 million deaths per year, which is attributable to the air pollution. So that's why this developing of the urban airflow related solutions is so important. But we concentrate also on the wind comfort and the safety, which are related to the pedestrian discomfort and the safety issues, and also providing policymakers necessary information to mitigate these negative effects. In terms of the urban building, we concentrate on the predicting energy consumption, thermal comfort, indoor air quality at the building and the urban scale, because HPC makes it possible. I mean, this bigger, wider scale of the simulation. We are integrating a different building stock with the environment. That's why collaboration with the air pollution model is possible. We are exchanging information about the heat, GHG, NOx. All this information are quite essential to properly assess quality of the air. In terms of the renewable energy sources, we concentrate on the estimating energy production from the wind farms and photovoltaic systems. We take the mesoscale predictions, recalculate it at the smaller scales, like 10 meters, and use it for the simulations. For this purpose, we use two models, WRF for the mesoscale weather prediction and EURAC for all-scale physical flows. It benefits with the improved accuracy of the weather predictions for renewable energy. Optimized placement and operation of the wind and the solar farms can be given to the investors. In terms of the wildfires, we enhance this model spread simulation by coupling fire behavior and atmospheric conditions, provide an analysis tool to assess the risk simulations in large fires, improve the understanding of the fire-atmosphere interactions. Again, we are working on different models, WRF as fire, open form, and it is very beneficial for the end users like firefighters, civil protection and units, including also regional administrations. In terms of the, it is a simulation, but unfortunately doesn't start. Anyway, in terms of the last but not least, our use case, material transport in the water, we are trying to predict how the sediment is transported in the water. We are coupling it with the information about the temperature effects, coupling with the hydrodynamic model with finite element computations using continuous and discontinuous Galerkin methods. There are many challenges here we are trying to address. One of them is environmental challenges, often involve complex interaction between water, solids and gases. This conventional simulations rely on the model simplifications with a certain closure relations, coupling between the phases, which require enormous computing power. All the simulations are deployed on the most powerful HPC systems across Europe. They are presented on the slide. It gives us another opportunity to make it more scalable in order to provide a better accuracy, to test the different scenarios using the ensemble scenarios aspects. Basically, that's it. Hopefully it was kind of encouraging incentive to listen to the next presentations from my colleagues from the project. Thank you.